Hello, everybody. Well, we've made it to the second fundamental theorem of calculus. This is going to be essentially the end of the first pass through the material, and it's a good stopping point for now. But of course, we're going to want to come back to this and add some more later. Pick up a few extra details we haven't talked about, and maybe handle a few details that we didn't prove. We just wrote down. So let's do it. Let's get to the second fundamental theorem. This is the one that you probably know the best from your Calculus 2 course, maybe even your Calculus 1 course. But we're going to write it down with a slightly weaker hypothesis than what you would see in a Calc 1 or Calc 2 course. All right, and that's going to make the proof a little bit different, but actually not like super challenging here. So first, we're going to have our function on a closed interval a, b to r. And we're going to assume that this f is differentiable with derivative, of course, f prime. Okay, when I say it's differentiable, I mean on the entire interval ab. And so this f prime will also have domain ab. Okay, so the fundamental theorem of calculus, the second one, is going to tell us if we know a little something more about this f prime, right? Not just that it has an antiderivative, but also that it is integrable, then we're going to be able to compute the integral by just looking at the original function f and evaluating the net difference on the endpoints. Okay, so let's write this down. So if f prime is integrable, then the integral of f prime on the interval ab is the net difference of this original function f on the interval ab. Okay? Or if you like, and this is the way you normally would see this, if you're trying to integrate some function and you know it has an antiderivative, then you can evaluate the integral by just evaluating the antiderivative on the endpoints and computing the net difference. Okay? And this is where people tend to mix up the idea of anti-differentiation and integration. Right? This statement right here is essentially telling you that in order to do integration, that's what this symbol is, you need to do anti-differentiation, right? That's how you get this f. And so people tend to conflate anti-differentiation and integration with each other. Rest assured, they are not the same thing. They give you the same answer, but they are not the same thing. Okay, now you say, well, they give you the same answer. Well, at least in this case, right? Now, there are absolutely functions we can write down that are integrable, but not anti-differentiable. And there are functions we can write down that are anti-differentiable and not integrable. And that's why they're not actually the same thing. They just give you the same answer. It's a lot like when we talk about multiplication being repeated addition. It's not. They're two separate operations. However, under the right circumstances, they give you the same answer. And so we often will treat them as if they're the same thing. Okay? Same thing is happening here. Now, I just want to point out this word integrable here is not the word that was in your Calc 2 course. In your Calc 2 course, they almost certainly use the word continuous. But of course, if we know our function is continuous, then it is integrable. The reason they likely did that is it's a little bit easier of an argument to prove this when you have continuity. Not to mention, you don't have to define integrability in this more general sense. Okay, so we're going to try to prove this second fundamental theorem of calculus. Okay, so here we go. So we're going to start, since we're going to do integration, we know integration has something to do with partitions, right? Let's start with an arbitrary partition. So we're going to let, say, x box, which will be x naught through xn, Okay, this will be a partition of AB. It's an n partition. Okay, and as usual, we'll define the subintervals I1 through IN. Okay. Now, we know that this function, the original function little f, is differentiable on the closed interval AB. And that means that it's continuous on the closed interval AB, or on any of these subintervals. Okay, so f differentiable on the entire closed interval AB implies f is differentiable and continuous, right? Because differentiability implies continuity on each I sub k, say. Well, once you have differentiability and continuity on the entire interval, then we can apply the mean value theorem. So by the mean value theorem, we know that for each one of these intervals, there's going to exist some special element, we're going to call it zk, such that the difference quotient across the entire interval ik is equal to the derivative of f at this one point, right? So the average slope is equal to the instantaneous slope at some point. So by the mean value theorem, for each k equals 1 to n, there exists some point, let's call it zk in ik, such that, and I'll write this just in a little different way than normal, f of xk minus f of xk minus 1. Normally I would divide here then by xk minus 1. I'm just going to move it to the other side. So this will be the instantaneous rate of change at zk times this xk minus 1. And of course, this bit here is just the length of I sub k. Okay, so I can tighten this up. F prime of zk times the length of I sub k. All right, now this product here is going to be great because this is showing up in our lower sums. All right, so this applies, well, let's see. If we do the lower sum, the f prime lower sum of this partition x, this is going to be, okay, well, it's a sum. K goes from 1 to n. I would need to take the infimum of f prime on the interval ik and multiply it by the length of ik. But now the infimum of f prime on the interval ik, well, let's remember that's going to be the greatest lower bound. That's necessarily going to be less than or equal to this f prime of zk, right? That was just one single point, and this is a lower bound. So this sum will be less than or equal to the sum of, well, let's just evaluate just at the zk's. Okay, but on the other hand, this f prime of zk being just one particular value of the f primes, that's actually going to be less than or equal to the supremum of f prime on the entire interval. So this will be less than or equal to the sum, k goes from 1 to n, of the supremum of f prime on ik times the length of ik. But this is exactly equal to the f prime upper sum of x. Now, in total, it looks like we've shown something that is not all that profound. The lower sum is less than or equal to the upper sum, and we kind of already knew that, right? That's true. But let's work down the middle now, right? Now, normally we don't go a third direction, but I now replace this f prime of zk L of ik with the expression that we have on the previous line. So this is equal to the sum, k goes from 1 to n, but now I can replace this expression with this difference, f of xk minus f of xk minus 1. And this is really neat. Okay, it's maybe not obvious at first when you look at it, but let's just do on the side here. When k is equal to 1, we're looking at f of x1 minus f of x0. Okay, what about when k is equal to 2? we would get f of x2 minus f of x1. And already you can see, look at this, the f of x1 and the minus f of x1 are going to cancel. And if we do another one, right, the next one when k is 3, we get f of x3 minus f of x2. And look now, f of x2 is going to cancel with the minus f of x2. So this is what's called a telescoping sum. The only thing that's going to be left at the end is going to be, well, this f of x naught with a minus, that never has anything to cancel with it. And then when you get down to the very end, you'll have an f of xn, and there's no next term to cancel that. So this is going to equal, at the very end, f of xn minus f of x naught. Oh, but xn, that's just the end of the partition, right? Like of the interval, that's just b. So this is f of b. And x naught, that's the beginning of the interval. So this is just f of a. So what we've shown now is that the lower sum is less than or equal to this f of b minus f of a. And, well, that should be really nice because that's the right-hand side here. And this f of b minus f of a is also less than or equal to the upper sum. But this was true for any partition, right? We didn't put any restriction on this. And so now we can finish this off. So this implies that if we look at the lower integral of f prime, so we know that this is equal to the supremum over all partitions. So we'll just take all partitions here of the f prime lower sum of the partition. But we just said that the lower sum is always less than or equal to f of b minus f of a. So the supremum must be less than or equal to f of b minus f of a. And similarly, f of b minus f of a is less than or equal to the infimum over all partitions w of the f prime upper sum of w. And this is equal to the upper integral. But our assumption, and this is where we need to use that f prime is integrable, right? Our assumption that f prime is integrable means that the upper and lower sums are equal. So since f prime is integrable, the lower sum has to equal the upper sum. Or integral, rather, right? The lower integral has to equal the upper integral. But if the endpoints are equal, right? If the endpoints are equal, then all the stuff in the middle has to be equal. And so this has to equal f of b minus f of a. And there it is. There's our proof of the second fundamental theorem of calculus. Okay, well, that's going to be it for now. We might come back with some more videos later on this stuff. There's some other things we did cover in the course that are quite nice. For example, we've spent this entire course talking about the real numbers, like we know what they are. And, well, maybe we don't. Maybe we need to give a precise definition. And there's some other proofs in the background that we haven't gone through. So hopefully we'll get to come back and finish all those off. All right, we'll see you in the future.